geometric quantization of b-symplectic and toric manifolds. Es decir, so we want to quantize. The idea is to geometrically quantize manifolds which are not symplectic but b-symplectic and have a toric action, which is kind of specific. Not all manifolds are toric manifolds. Not all b-symplectic manifolds are toric b-symplectic manifolds. So we are setting ourselves in. We will be setting ourselves in some specific subset of b-symplectic manifolds, which are b-symplectic toric manifolds. But I will explain exactly which are these manifolds, and I'm sure you have already an idea, which is that they have an action which is toric acting on them, and this toric has to be half of the dimension of the whole manifold. So if I have a 2n manifold, I will require that I have an action of a torus of dimension n acting on them in a Hamiltonian and effective action, basically. But first, let's start with some basic definitions, some previous definitions on geometric quantization. So to begin with, we will introduce geometric quantization, which involves a few steps. For instance, pre-quantization, and then which is formally quantization. And after seeing what is geometric quantization for symplectic manifolds, we will see a new model in which I am working and I'm defining on geometric quantization of b-symplectic and toric manifolds. So we will use the same ideas on geometric quantization, the same already existing ideas and existing results and theorems of geometric quantization, in order to see how can they be adapted to be also useful to compute some geometric quantization in the branch of b-symplectic and toric manifolds. So to start, the big idea of quantization, of geometric quantization in this case, is to transform a symplectic manifold to a Hilbert space, which will be the quantization space. And you would think that essentially what you are doing is, apart from transforming a manifold, a general symplectic manifold, to a Hilbert space, you also want that functions, smooth functions on the symplectic manifold, are mapped to operators in the Hilbert space. Now, if you are a physicist, what you want to have at the end, if you are a quantum physicist, what you want to have at the end are observables, and observables are mainly eigenvalues of operators. So basically, you want to have operators, and then from these operators, you can compute, for instance, observables. So you want to pass from a classical system, which is a symplectic manifold, for instance, with an iterable system, to a Hilbert space in which you will have functions transformed to operators. And then you can compute, for instance, eigenvalues of these operators, which are physical observables at the end. So at the end, you can think you are doing physics. So you need to do this quantization, this transformation for a symplectic manifold to a Hilbert space. This can be done in a lot of ways. So this quantization can be done, for instance, in geometric quantization. You do it in a certain way. In deformation quantization, you put the focus in other things, maybe not in the operators, but in other parts of the quantization. But in this case, the procedure is the following: is to take your manifold and add a few additional structure. You have to cube it with a few additional structure to be able to quantize it effectively. So let's see which is the structure you have to add to the manifold. So you have to add some structure always to properly quantize it. And this step of adding this structure is called pre-quantization. You have to add to your manifold some additional structure. So you already have to your manifold, which is normally a b-symplectic manifold. So you already have some structure, which is this omega, a symplectic form, but you have to add some additional structure which is basically a complex line bundle and a connection. So you add a complex line bundle and a connection. And this connection is defined on the line bundle. So this is a connection on L, which has to satisfy some condition, which basically is that its curvature has to be precisely omega. So the curvature of this connection has to be omega. And this is not absolutely general, so this is not the most general case, because you can have manifolds which cannot be quantized, but basically is that if the class of omega is integral, you can find this connection such that the curvature is precisely omega. And then you have quantized your manifold. If you can do these two steps, you can pre-quantize your manifold. So now you have your manifold pre-quantized. So now you do not only have m omega, but you also have m omega L, your line bundle, your complex line bundle, and a connection defined on the line bundle. So this is for a general symplectic manifold that you want to quantize, to geometrically quantize. If you have a toric symplectic manifold, you would also have a toric action of degree n and a moment map of this toric action. But before introducing toric actions, let's see how geometric quantization does continue from this pre-quantization that we have here. So the next step would be consider sections on this line bundle. So now we have L defined over M, and we want to consider some sections of this line bundle. We want to consider the set of sections, so complex sections of this line bundle. And when people do this, they find that there are too many sections. So we have to impose now another step in the quantization is to impose some kind of restrictions. We will not consider all the sections on L. The space of sections on L is too big. And so we will have to impose some restrictions, some special condition to consider only some of these sections, a subset of this big, very big space of sections on L, which are complex sections. And so consider sections on L and let's say impose a restriction to reduce this space. To reduce this space. And how can we reduce this space of sections, which is the rule that we will impose here? There can be many. This is the point. So now we will impose a restriction, which is kind of arbitrary and is related with the purpose of our quantization. So one possible restriction could be imposing a Kähler polarization. Another one could be imposing a real polarization. In general, the restriction to some special sections on L is done via a polarization. So you do this considering a polarization. So this is done with a polarization of L. And there are a lot of possible polarizations. So now Angel is entering, sorry. Hi, Angel. Let me see. I don't know if Angel could enter.
I cannot see him.
No?
No, yeah.
Yeah. Okay. Hi, Angel. Okay. So this is done with polarizations, and one could take Kähler polarization, and then this would give Kähler polarization, for instance, would give us a quantization via holomorphic sections. So if we only consider sections which are tangent to the Keller polarization, we would end up with only the holomorphic sections. We could also consider real polarizations, which is what we are going to do, in fact. And with real polarizations, what we end up having is only Lagrangian submanifolds of M. So if we consider real polarizations, what we have at the end is a Lagrangian fibration. So a real polarization you can see it as the fibration given by for instance, an interval system on M, and this will give us a real Lagrangian manifold. So we will end up with a Lagrangian fibration which we can think that is given by an interval system, for instance.
Polarization doesn't always mean an integrable system, or does it? I don't know what polarization
not always. But for instance, in our case, in the toric case, we will take the polarization given by the fibration of the moment map of this action. So not always. You are right. So it's not always this automatic, but a real polarization is when you have an integrable system, not the opposite directly. But if you have an integrable system, you have the real polarization associated to this integrable system. What you have, in fact, is that. Remember that we are doing this to restrict to a smaller space of sections, and the sections we will consider are not all the sections on the line bundle, but only the sections which are tangent to the polarization we are taking. So if we take a polarization given by an interval system, we will be taking sections which are tangent to the fibers of this interval system, basically. But yeah, this is a good point, because we will be using it the other way. So we will take an interval system. In fact, we will take a moment map, and we will consider the polarization that arises from this moment map, and we will consider only sections which are tangent to this polarization. So now we have a smaller space which is made of sections which are tangent to the polarization, which are not all sections, only the tangent ones, let's say.
But my question is also, what is a polarization? Is it a foliation that is?
Yes. So if you have a vibration over, let me write it. If you have a vibration, for instance, if you have a vibration, for instance, from a manifold to some space, you can consider the distribution associated to this vibration and the tangent space. So the polarization, in some sense, is a subset of the tangent space of M. So you will be considering only. So this is the polarization. You can think of it as part of the tangent space. So if you have an interval system, this pi is not a general vibration, is specifically the moment map, for instance, of an interval system.
And do you ask that the sections of the polarization are closed under the Lie bracket, or that is not necessary?
I asked some things that I'm not saying. For instance, that fibers have to be compact. I'm asking polarization. So in fact, this moment map I'm asking that it has compact fibers. And even more, I'm asking that now the sections that I will consider are tangent to this polarization. So this polarization you can think as a distribution associated to this projection, to this vibration of given by the moment map.
Okay.
And I'm asking that fibers are compact, but this is quite general because in integrable systems, all regular components are compact. So this is quite a normal thing to ask, that it has compact fibers. So when you have this reduced space of sections, now you will look for sections that satisfy this condition as an equation, which I will call flat sections. Then you look for flat sections. So from among these sections, then the next step is to look for flat sections. And now I will define what are flat sections. We look for flat sections or leafwise flat sections. So we have vibration, we have leaves or fibers associated to these vibrations, and on these leaves, which are the leaves of the polarizations, we are going to look for sections which are flat on the leaves, and we will see what's the meaning of being flat on a leaf of the polarization. And we look for flat sections of this polarization. So flat sections of a polarization are sections that satisfy this condition. So flat sections sigma, which basically satisfy, namely sections that satisfy the following condition, that mainly I could say that are covariant constant with respect to the connection we had on L, the line bundle, that are covariant constant. And I will write explicitly what means to be covariant constant with respect to the connection we had on L. Or equivalently, that sigma has to satisfy this equation for any x in the polarization. So this is where we see that we need the polarization because we are considering solutions of this equation that are only tangent to the fibers of our moment map, if you can see it this way. And then among these all possible sections that are tangent to the fibers of our moment map, we're going to look for the set of sections that, apart from being tangent to these fibers, satisfy this equation, are covariant constant to this connection, whose curvature was omega. So we really need all the ingredients presented up to now, and this set of sections is really special. So this set of sections that satisfy this equation, so this set of flat sections sigma that we have here do form a sheaf, and this is really important because if you know that some set forms a sheaf, then you can, for instance, compute a cohomology, the sheaf cohomology. So it was discovered that the set of sections satisfying this condition, so the set of flat sections, is a sheaf. It's not a general set. It has a structure. It has the structure of a sheaf. And if you have a sheaf, you can construct a cohomology, the sheaf cohomology, and from this you can define the quantization. So now we arrive to the definition of the quantization, and it's the following. I will call it J. So J will be the sheaf of flat sections. And from a sheaf of flat sections, if you consider the sheaf cohomology, in which I will not enter, but well, I could devote another session. I could devote really an entire hour defining how a sheaf cohomology is defined, because sheaf cohomology is kind of a technical and specific procedure, which is kind of well known by topological algebras, but it's kind of a useful tool, and in fact, it's useful to define geometric quantization. Why? Because geometric quantization is defined in the following way. If you have J as the sheaf of flat sections, now the quantization of a manifold is defined as the sum of all the cohomology groups from 0 to n, well, to n, well, you can count them out, of m with respect to this sheaf of flat sections. And this is the homology groups associated to the sheaf cohomology, which is which might not be easy to compute. So at this point, the natural thing is to observe that the quantization of a manifold in general can be difficult to compute via this definition. So this definition does not give us a direct way to compute the quantization, but it's telling us that we should compute the cohomology groups associated to the sheaf cohomology, and then we would sum. If we sum all of them, we have the quantization of our manifold. What is interesting and what allows us to compute geometric quantization effectively in many cases is a theorem by Snatitsky, which in some sense allows us for a shortcut to arrive to the quantization. So this could be difficult to compute, but we have a shortcut. We have an easy way to compute the geometric quantization of a manifold in general. To compute Q of n, which is the geometric quantization of m. And it basically has two steps. One of the first step is to use a theorem of Snatitsky, which essentially tells us that all of these cohomology groups are 0 except by 1. So basically, Snatitsky solves for us the computation in all the groups. This is due Snatitsky in 75. So Snatitsky tells us that all cohomology groups in the sheaf cohomology are 0 for all the k different than n, and even more, it tells us which is the number of, well, which is the dimension of the group of dimension n. So the group of dimension n is not 0, and Snatitsky's theorem also tells us which is the shape of this group, and this is essentially the sum of copies of C of the complexes to the m, and m is the number of Bohr-Sommerfeld leaves, which is a thing I have not defined yet, but we will see which is this. And this is a finite number or not, but this is a thing that we would like that it's finite, and this m we pure sure that this m is finite. So this m is the number of Bohr-Sommerfeld leaves, and now we will see which of the leaves of the vibration are Bohr-Sommerfeld leaves, in fact. Yes. So the first step to compute, the first step in the shortcut to compute the quantization of a manifold is first to use Snatitsky. Snatitsky tells us that basically the quantization of a manifold is C to the m, so C to the number of Bohr-Sommerfeld leaves. That I will define now what are Bohr-Sommerfeld leaves, but essentially is to count the leaves of the vibration which satisfy the Bohr-Sommerfeld condition. And now we will see which is this condition. But basically, the shortcut is only to consider to look for. Sorry, yeah.
Sorry, I have a question.
Yeah.
And when Jay, when your polarization is the Keller polarization, what I know is that you obtain holomorphic sections of the line bundle of the holomorphic line bundle, but this is H naught. Is not H2 in the case of surfaces or something like that. So how is this related with what I know?
So in this case would be H1, no? Because this n, so this n is, so the manifold is m to the 2n.
Mm-hmm.
So this n is half of the dimension of the manifold.
Okay, but again, this is not H naught, which is what I will expect.
Okay, so you are saying that this is different from Keller quantization. Yes, and it is.
Okay. So this theorem always only applies for real quantization, not for.
Yes. This is for real polarizations.
Okay.
Yes.
I
So
thought that this was useful for all the quantizations. Okay, perfect. Okay. Thank you very much.
Sniatycki's theorem is for real polarizations, and yeah, you have to count now the number of Bohr-Sommerfeld leaves, which will give you the dimension of the quantization space, basically. So Bohr-Sommerfeld leaves are the important leaves here. So let me change slide. And Bohr-Sommerfeld leaves are the following leaves in the polarization. So a leaf of the polarization or of the vibration is Bohr-Sommerfeld if there exists a flat section on it, which is globally defined. So we knew there are flat sections, but this characterization of some leaves tells us that we have to look not for all the sections in all the leaves, but only we have to look for leaves in which we can find a global flat section. So a leaf of the polarization is Bohr-Sommerfeld if there exists a flat section defined globally on L. And then we would call L a Bohr-Sommerfeld leaf. So if we can find a flat section in L defined globally, we say that it's Bohr-Sommerfeld leaves. And generally, this fails in most of the leaves. We cannot find a flat section defined globally. We can always find it locally. But what happens is that when we want to, let's say, connect it via a complete, if we take for instance, we have a sphere and we have a leaf. We have a polarization, the real polarization of the two sphere given by rotations, which are latitudinal circles. What happens is that in general, flat sections that solve the equation, sections that solve the equation, so flat sections, are only defined globally in some specific latitudes, because in almost all the latitudes, what happens is that the angle doesn't match when we take the entire loop around the latitude circle. So what happens is that this fails. You cannot define it globally because you have let's say a multi-valued function, which is the angle, except at some points, at some latitudes, in which it matches. And in this basic example of the sphere, you can see that when it works well, when you have a section defined globally, is when some angular parameter is an integer, because if you think as in polar coordinates, the exponent of in the exponential where you have the angle, if you have an integer, it matches well, and the let's say the imaginary part it disappears, and you have a well-defined function on the circle. But you only have this satisfied in some discrete set. So in this set of Bohr-Sommerfeld leaves in general discrete. So this is this idea is what allows us to see that this M, this number, if the manifold is compact and you don't have cumulation points, would be a finite set. So in general, Bohr-Sommerfeld leaves is a discrete set, but in particular, in most of the manifolds, is a finite set. A part of discrete is finite. So this is a really good method for quantization if we are looking for results which are finite dimensional, which are kind of natural if we came from a physical problem and we want to have in which we have finite compact manifolds, and we want to have finite results, so finite dimensional results, I would say. So we have Bohr-Sommerfeld leaves, which are the leaves in which there exists flat section defined globally, and quantization is given by essentially C to the number of Borsommerfeld leaves. But there's another step in the shortcut which allows us to find Borsommerfeld leaves, because Borsommerfeld leaves maybe are easier to find than to compute the cohomology groups, but still there is an easier way to compute quantization, which is given by a result. So the second step in the shortcut, I will not spoil it without writing. The second step in the shortcut will be the following. Would be to use a result from Gilliam and Steinberg, which tells us the following, which tells us how to find Borsommerfeld leaves. So this following result from Gilliam and Steinberg tells us that essentially Borsommerfeld leaves correspond to the integer lattice. So Borsommerfeld leaves correspond to the integer lattice in the image of the moment map. And this is the way to find which is a quantization, because it's now this is easy. This is the only step that we can. Okay, let's go and compute it. Okay, you can go to the moment map and compute the points which have an integer image. So which have an image which belongs to the integer lattice. So this second step, together with the Sniatich's theorem, tells us how to compute the geometric quantization of a specific symplectic manifold. So you have to go, this is if you have this real polarization given by an interval system which has a moment map. In this case, you can go to the moment map, look for the integer lattice, and look for the points in the moment map which belong to the integer lattice there, and then each point in this vibration. So this point corresponds. Each point in the moment map corresponds to a leaf of the original manifold. Each leaf corresponding to one of these integer points of the moment map is a Borsommerfeld leaves. And if you count the number of integer points, it's the same as counting the Borsommerfeld leaves. So you are counting essentially the dimension of the quantization space. So this is the second step in the shortcut to compute geometric quantization of a general symplectic manifold. So this is essentially the result we classically have to quantize geometric manifolds. So essentially, quantization, this is not super rigorous, but essentially quantization, I could write that quantization of symplectic manifolds is the same as counting Borsommerfeld leaves. And counting Borsommerfeld leaves is the same as counting integer points in the moment map. So basically, it's counting Borsommerfeld leaves, which now we know that correspond to the integer points in the image of the moment map. This I prefer to say the integer lattice, not the integer points, because the moment map lies in the space which is half the dimension of the manifold. So all the components has to be integer. This is why I call it integer lattice. But in dimension 2, essentially they correspond to integers. So in dimension 2, we have a moment map which lies in a one-dimensional space, and the integer points there give us the Borsommerfeld leaves in the original manifolds, essentially. So this is the picture we have. Well, this is a super brief the plot of the picture we have for symmetric quantization, but now we want to put the focus on geometric quantization, not of symplectic manifolds, but on b-symplectic manifolds. And on b-symplectic manifolds, what we have is the following problem. So in b-symplectic manifolds, we essentially, if we wanted to do the same procedure, we would have the following problem. So
sorry, I have another problem before.
Yeah, sorry. Yeah.
Thank you very much. I have a question. The key is Can you say explicitly the isomorphism between the Hilbert space associated to the real polarization and this set of Bohr-Sommerfeld fibers? I mean, if you give me an element of C up to rise to the number of Bohr-Sommerfeld fibers, can you give me the section, the element of the cohomology associated to it? Is it a explicit isomorphism, or is just a kind of theoretical isomorphism?
This is, in fact, this is explicit. I mean, for instance, if you, for instance, you can write explicitly the equation of the flat sections. This you could read this as isomorphism. I mean, yes, you can the equation. I mean, yes. So the sections.
I'm concerned with that because quantization, geometric quantization, for me has a kind of physical meaning, and this quantization in terms of Bohr-Sommerfeld fibers doesn't. So that's why.
Okay. So you are in the opposite situation as me, because yes, for me, I normally find that I cannot relate what I know mathematically about geometric quantization with physical problems. So we could discuss it in some day, because I would love to see which is the physical which is the physical real counterpart of these mathematical definitions we give on mathematical models. So this is a really interesting point, because we have an explicit form for the flat section. So we know which are the Bohr-Sommerfeld leaves. We know the equation of the equations. Sorry, the equation of the sections that are Bohr-Sommerfeld. So I can write them here. So basically, are of this form. So I will write them in 2 dimensionals, which is the easy case. So for instance, in 2D, there's only one case, because you can have the sphere. I will put myself in the toric case. I don't know if, I mean, I will do it in the toric case because I don't know it by heart the rest of it, but they all of them come from the toric case in 2 dimensions. So in 2D, in the toric case, basically you only have the cylinder and the sphere. And you can think on the sphere, you can think about the sphere as a compactified cylinder. So let me write explicitly the equation of the flat sections in the cylinder. In the toric case, let's consider the cylinder. Consider the cylinder with cylindrical coordinates, no? With cylindrical cylinder given by h theta, for instance. So yeah, we have an equation for the flat sections, which is this one, which is e to the I h theta. This is the general form of the flat sections, but you have to require, and this is the important point, that h is an integer. So for the cylinder, this is for the cylinder. You have this. This is the shape of your space, and this is any complex function. This a of h is a complex function of h, not of theta, only of h. And now notice that in this case, what we have in this, now where I should draw a picture in the cylinder. So we have a cylinder with rotations. We have theta as the angular coordinate, h as the height coordinate, and Bohr-Sommerfeld leaves are leaves in which h belongs to z. So these are the global flat sections defined on a Bohr-Sommerfeld leaf. This is a Bohr-Sommerfeld leaf, is a leaf for a fixed h. Is h equal to h0 with h0 belonging to z. So if you fix h, if you place yourself in a leaf, the h is fixed. So in fact, this map and you can see the reason for this integral condition. This section has a constant here, a complex constant here, and this matches well. So this, well, I should add here the 2 pi, sorry. If you have that h is an integer, then you see that this works well for the angle. So the angle matches when you do a loop in this cylinder. So from this is where it comes this integer condition. So a Borsommerfeld leaf is found at any integer h in this case. So this is Borsommerfeld, this is Borsommerfeld. The zero leaf would be Borsommerfeld, etc. So the isomorphism you have at the end is that Q of M is isomorphic to C to the M, because this C, this space, this module, this space of functions is exactly accounts for all these possible functions you can have here. So you can have here any complex value. So this A of H is the freedom you have, is what gives you this complex space. And you have this for each Borsommerfeld leaf. So since you have, you can have this infinite number, but this complex infinite number of constants multiplying here for each flat section. So this each flat section has this form at each leaf. So for each leaf, you have a choice in the space of the complexes of this parameter. All of them allow us for a globally well-defined flat section. And since we will have, so if we consider a manifold in which there are m integers, so if we cut the cylinder at some point, we will have m integers, and for each one we would have this copy of C. So this is the origin of this. Well, I don't know if you're asking exactly for this way of explaining the isomorphism, but yeah, essentially is that this copy of C comes from the freedom you have here at the choice of this complex constant multiplying in the flat section equation.
Yeah. I see. Perfect. Thank you very much. Yeah, you're right. This is very, very explicit. Yeah, perfect.
Okay, so it's nice that you have this and that you could already see
Thank
this
you.
feature, because
I'm sorry. I apologize that, Pau. I'm sorry. I'm very late in your talk because I was discussing the problem of contract with Alberto, and out of the sudden, Alberto and I realized, we are late for the talk. I'm sorry. I apologize, and it's my fault that Alberto was late too. I'm sorry.
Hi, Alberto. Hi. So now let's see how can we try to do the same with a b-symplectic manifold. So let's start with a b-symplectic surface. Let's take the sphere. Let's take the easiest case. Let's take the sphere, the b-symplectic sphere with Z on the equator. So let's consider now the b-symplectic sphere, and let's consider also a rotation. So let's consider a toric action here, the rotation, which is given by, well, in this case, S1, the rotation around the vertical axis. So let's consider this, which we call it the b-sphere, the canonical b-sphere, with an action given by rotations, which is the S1 action, given by rotations around the z-axis. This action is essentially the same that in the symplectic case. So in the symplectic case, we were also considering this rotation action, but now we have an action in this b-symplectic sphere which is compatible with Z, because Z is a latitudinal circle, and these rotations also move the sphere latitudinally, let's say. Rotation around this z-axis. The point here, the new point here is that if we want to quantize it, now we know that if we wanted to do the same that in the symplectic case, we would go directly to the moment map of these actions and to compute there the integer points. It would be as easy as this. But in this case, we have a critical problem here, that is that the moment map in this case, even that it is a compact manifold, the moment map goes to infinity. So we have a problem. Just to start, we have a very big problem, that is that we want to count something, which is the integer points, which we know that is infinity. And let's see why. We have an infinite number of Born-Sommerfeld here. If we start doing the same procedure as before. So now if we compute the moment map of this, let's say that this is the sphere that goes from -1 to 1, the classical sphere, and the moment map here would be minus logarithm of h. And what happens with minus logarithm of h from -1 to 1? What happens is the following. If we consider h from -1 to 1, we know that at the -1, so the moment map, the image of the moment map, let me start drawing with colors, because this would be the key point. Let's see that the image of the moment map of -1 of this singular leaf, okay, I've not mentioned here until now, but here we have a polarization by a real polarization given by this rotation, and all the leaves are one-dimensional except for these two leaves. The leaves in the north and south polar caps are leaves which are one-dimensional, are points, sorry, zero-dimensional are points, but still are leaves of the polarization, and they could even be called and be Born-Sommerfeld leaves, singular Born-Sommerfeld leaves, but still Born-Sommerfeld leaves. Okay, they are different, they're special, because if we want to consider them for the polarization, we have to take into account that they have different dimensions. But we can also think of them as leaves of the polarizations, and even if we find that they correspond to an integer point, as Born-Sommerfeld leaves. So in this example, for instance, the moment map at -1 is 0, and then goes up to infinity if we go up in the h direction. So if we consider different latitudes from -1 to 0, the moment map minus logarithm of h goes to infinity. And on the other way, the same happens if we start in the North Pole and go down. So the moment map in this case goes to infinity. And this is a problem, well, or not, but this is a problem if we want to count Born-Sommerfeld leaves and obtain a finite number, because we can do it. We can count the number of leaves that are that have a moment map value which is integer, but we will end up with an infinite number of Born-Sommerfeld leaves. And this is the thing that physically, and this, I'm sure, Angel, you would give more intuition, more sense to this, that physically we don't want that a quantization in this case gives us an infinite dimensional space. For some reasons, we want, or it is more natural to obtain a finite dimensional Hilbert space. So we will have to do to define some model which can count this and end up with a finite result, with a finite number of Born-Sommerfeld leaves. And which is the idea? The idea is that for each Born-Sommerfeld leaves here, for each, let's see that is, okay, let's assume that this is an integer, 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 etc. So which are the Born-Sommerfeld leaves we have here? We have one Born-Sommerfeld leaves here, which is in this H, so would correspond to this would be a Born-Sommerfeld leaves. We have another, sorry, no, this is in the, let me draw it properly. This is in the South Pole. Let me draw it properly. This would correspond to a leaf here. Then the next Born-Sommerfeld leaves would be placed here. The next Born-Sommerfeld leaves would be placed here, and there's an accumulation. Now here there is an accumulation of Born-Sommerfeld leaves here next to the equator. There are infinite Born-Sommerfeld leaves when you are close to the equator, and the same happens in the north cap. Let me finish drawing the sphere. Sorry, the upper singular surface, and then you have a Born-Sommerfeld leaf here. You have another Born-Sommerfeld leaves here. But here you have an accumulation of Born-Sommerfeld leaves when you approach to the equator. And you have an infinite number of Born-Sommerfeld leaves because essentially at near Z you have the smaller is, I mean, it doesn't matter how small is the neighborhood you take consider that in this neighborhood you have an infinite number of Born-Sommerfeld leaves. Specifically, if you consider, if you take a look at the moment map at the neighborhood of 0, you have an infinite number of Borsommerfeld leaves, because the image of the moment map goes to infinity, and then you have an infinite number of integer points here. What can we do? Now, what can we do to surpass, or to avoid this problem of infinities? We can think, and the idea of painting it with Barça colors, which are not Barça colors, but the idea of painting it in blue and red is to think that on the North Pole we will count them with a sign, and in the South Pole we will count Borsommerfeld leaves or integer points with the opposite sign. And a number with a sign and the same number, or another number with an opposite sign, even the quantities in different sides are infinite. When we add them together, the infinite will cancel if we are summing them with opposite signs. So now the idea is to count Borsommerfeld leaves or integer points, but with sign. So we will count positively for instance, in this case, we will count positively the Borsommerfeld leaves in the southern cap, and negatively the Borsommerfeld leaves in the northern cap. In this case, and now this is a question for all of you, which would be the quantization of this symmetrical example, which is the sphere with Z on the equator, if we count the number of integer points in this way, positively in the southern hemisphere and negatively in the northern hemisphere? Which is the quantization do you think it would give us this model of counting it positively and negatively?
Romero needs to know the answer.
Well, maybe the question is so silly that you cannot think that I'm asking this, no? But the quantization in this case is 0.
So if they ask you for a number, it has to be a universal number.
So
otherwise,
in this supersymmetric case, it is
1,355. It wouldn't be the case.
Exactly. Why is it so simple? Because if we count it with sign, and due to the symmetry of this example, and due to the symmetry of the moment map around 0, basically, for each positive Borsommerfeld leaf, we have its corresponding negative Borsommerfeld leaves in the other hemisphere. So essentially, these Borsommerfeld leaves is cancelled. So let me try another color. These Borsommerfeld leaves cancels with this Borsommerfeld leaf. These Borsommerfeld leaves cancels with this Borsommerfeld leaf. There's a cancellation in each Borsommerfeld leaf because there's an
we have an answer from the public. Angel has replied to your question using the chat.
Okay. So.
It's just a joke. It's just a joke saying that.
Yeah, exactly.
Okay.
No, but the joke has the right answer, indeed.
Could be. You never know if 1 over minus 1 over 12 appears somewhere. But in this simple case, it would be 0. Okay, but it's due to the symmetry of this problem. But in more complicated b-symplectic toric manifolds, the situation has to be approached with more caution, let's say, because we can have a sphere. In general, a b-symplectic sphere can have more than one connected component in Z. So this, I'm going to draw another example. This could also be a b-symplectic manifold, a b-symplectic toric manifold, and a b-sphere. But a more complicated, not the easiest b-sphere, but it's still a b-sphere in which we can still have a rotation. Let's consider this. Well, this is the disjoint union. Well, the union of this Z1. Let me start from the bottom. Z1, Z2, and Z3. So this Z in this case has 3 connected components, 3 latitudinal circles, and in this case, this sphere is made of the b-sphere without Z is made of 4 connected components. So M minus Z, let's see. M minus Z is made of 4 connected components, which I would call S0, the south polar cap, S1, the first band, S2, the second band, and S3, the north polar cap. This is made of 4 components. And which is the moment map of of a rotation in this, of which could be a moment map of a manifold of an action here in general. So an action here in general could be, for instance, could have the following moment map. Let me draw a possible moment map for this manifold. Let's still assume that we parameterize it from -1 to 1 in the h coordinate. And let's see that the moment map at each z goes to infinity. And of course, it goes to infinity for the same reason that it has to, well, at z, it goes to infinity. We know this is proved, for instance, by Eva Miranda here, which the moment map at the singular hypersurface goes to infinity. But at the rest of the manifold, it has a finite value. So at hz1, hz2, and hz3, this goes to infinity. But in the other parts of the manifold, in the other leaves, it doesn't go to infinity, and for instance could do something like this. Well, no, not that much, because, sorry, this last one, for instance, like this. This could be an example of a moment map here. And now, if we were going to look for the Boltzmann leaves here, so which are the circles of the polarization which have an integer value of the moment map, we will again find that they are infinite. But now is when we do the trick of counting it positively and negatively depending on each side of Z or on each band they are. And the trick is to start alternating signs here. So this will be positive. We would count the Boltzmann leaves here negatively, and here also negatively. And what happens here, that if we look for Boltzmann leaves here, we find that, sorry, no, this corresponds, let me write, this is S3, this is S1, this is S1, this is S3, and this is S2, and this is S0. In S0, we could have, for instance, this Boltzmann leaves at this integer height, this Boltzmann leaves at this integer height, this Boltzmann leaves here, and an infinite number up there. And also, here we'll have a Boltzmann leaves here, 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 and an infinite number of Boltzmann leaves on each component. And on the other components, in S1 and S3, we also have Boltzmann leaves, but essentially in the same heights, sorry, in the same values of the moment map, but at different ages, for instance. Now, what happens if we count them with sign and cancel? In the count, almost all of them are cancelled, and this is the key point. So, okay, we have 6 infinities here. I mean, we have 6 subsets which go to infinity, which are this one, this one, this one, this one, this one, and this one. But the number of Boltzmann leaves here, counted with sign, is cancelled. So the point is that, okay, all these infinities here are cancelled. Let me take green color. Let me draw it in green. Okay, here there's a cancellation, here there's a cancellation, a cancellation, a cancellation, and an infinite number of cancellations. Here there's also a cancellation, and here, and here, and here, and here. And here there are also infinite cancellations. So at the end, what are we left with? We are left with only a finite number of Boltzmann leaves. Let's say this one, and this one. So the quantization of this manifold at the end, okay, there we have infinite number of Boltzmann leaves here. I will not find, well, I will find them here. I mean, we have infinite number of Boltzmann leaves here, and here, and here. But at the end, the only blue Boltzmann leaf that has survived are 2. Well, in fact, there are 2 leaves surviving here, which is, one is around here and another one is around here. These, for the moment, have not cancelled. And then there's a red surviving Boltzmann leaf, which is in S1, so would be here. there's an infinite number of red Boltzmann leaves here and here and here, which have cancelled. So let me draw a nice, an ugly cancellation, but this is a cancellation. Here it happens another infinite cancellation, and here it happens another infinite cancellation. And we are only left with 3 Boltzmann leaves, 2 positive and 1 negative. So at the end, with 2 positive and 1 negative, we can still consider this a last final step in the cancellation, and which would be the quantization of this manifold. Again, this is not that simple as before, but almost the quantization, which I have not defined now rigorously. We are writing it, and technically in our LaTeX version of the paper, it would be written like super technically with coordinates and with subindex and everything. But without having defined it technically, you can already see that the quantization in this case is C to the 2 minus 1. So C to the 1. Because there's 2 positive Boltzmann leaves here, the blue ones, and 1 red Boltzmann leaf here in S1, S3. So this is a model which is kind of more general. It is useful for b-symplectic spheres in general, for b-symplectic torus in general. And with this model, we can end up with a quantization which is finite, which that will be the next step, give a physical sense to these results. So, okay, we know that we prefer finite results for the dimension of our quantization spaces. Now we should discuss why, and I'm sure that here, from people here, Angel knows a lot, because this was your previous question. I will end now my presentation here, but just to say that this quantization model, apart from looking for a physical interpretation, maybe you could say, we already know that it can be proved that it is equivalent to another quantization model, which is far more abstract, which is formal geometric quantization. So we are in the way to prove that this quantization model for b-symplectic manifolds is equivalent to the formal geometric quantization of b-symplectic manifolds, which is another model which was introduced by Jonathan Weizmann and others, and we are trying to prove that this model given by this strange quantization with sign, which is not that strange, it matches well, it fits well, and it's in fact equivalent to the model given by formal geometric quantization, which I'm not going to explain today, but would allow us to speak of it in another session at some point, I hope. So let me end here, and now it's the moment that you can ask more questions if you have it, and thank you all for being here today.